Okay, want to do another energy problem. This time we're going to go up an incline. So we have a spring that's loaded against the ball. Okay, and the spring is compressed, has a compression distance equal to, if you read the problem, I believe the compression distance is 35 centimeters, so that's 0.35 meters. Okay, 0.35 meters for the compression distance. And I want to move that down here. Okay, so we've got the compression distance. This uh, incline is at an angle here. Some angle, let's call it theta. Theta. And the ball is going to go from this point to some distance. Let's copy, paste it. It's going to go to some height up here. It's going to go up slope some length and some height here. We don't know what the height is. That's some height. And it's also some length up the slope, right? This is also some length up slope. So from here to here, you've got some, let's do a lowercase l, length up the slope. Now, this incline has friction involved, okay? So there's some bit of friction, and we know what the coefficient of friction is. Fantastic. Uh, so this is an energy problem. And we can set up energy down here at this spot, energy at this spot. We can determine how much work is lost due to friction, and then we can solve the question of how far up slope it goes. So first off, set up your conservation of energy equation and include work. So our energy equation is all your initial energy before is going to be equal to all your final energy plus whatever work went out of the system. Okay, so plus whatever work left the system. As we look at this and analyze our initial spot, this sphere isn't moving. The sphere is not moving, so the initial kinetic energy is zero, translationally and rotationally. Okay, they give you the stuff for rotational kinetic energy, but you really don't need it. This kinetic energy is zero. Okay, initial translational and rotational kinetic energy are both zero. And as this thing rolls up, it's going to come to a stop. It's going to come to a stop when it reaches the farthest length that it can go up. So the final kinetic energy is also zero. Now, potential energy initial, you might be inclined to say, oh, well, that's zero. But you can't because there is a spring involved. Okay, there's a spring involved. So what we have over here is potential energy. This makes up potential energy uh, gravitationally plus potential energy due to the spring, or the elastic potential energy. And now, yes, we can say the gravitational is zero. So over on the left side of your equation, you're going to have potential energy due to the elasticity of the spring. And over on the right-hand side, we'll have the gravitational potential energy gravitational final. Remember, this was initial. And the final, and then after it's released from the spring, there is no elastic potential energy in the final position. But you do have the workout, and workout is due to friction. Okay, so what does our equation look like? We have initial potential energy due to the elasticity of the spring. That's going to be equal to our gravitational potential energy due to the height that this ball reaches, plus whatever work we lose. Subbing in our formulas, we'd get the following. We get our formula for elastic potential is the K constant times the spring displacement squared over 2. Potential energy gravitational is mgh. Workout is going to be due to friction times however far that travels upslope. So we need a way to find friction, and we need to find a way to determine the height, because we have this information and we can find K. Okay, we don't know K, but we'll have to figure out a way to find K also. So let's start out with the friction. And this is a bit of review, but we have a force normal acting on this ball as it rolls up the ramp. We've got force of friction acting against it. So here's your friction. And here's your force normal. And you have your weight acting downward, right? Acting down. Let's try and make that look a little. Your weight acting downward. So if you tilt, we can tilt our axis like we've done in the past, where we have our x and y axis this way. We know this angle in here is equivalent to theta. So force normal is equal to our y component of weight. Force normal is equal to the y component of our weight. And the force weight in the y direction is equal to force weight times cosine of this angle. And it's cosine because this angle is equivalent to this angle, and we're measured from the y-axis. So cosine of theta, and that's equal to our force normal. Why am I trying to find force normal? Because force of friction is equal to mu times force normal, the coefficient of friction times force normal. So I can take this information and plug it in here. Force weight is mg. Force weight is mg, so I'll plug that in. So force of friction is essentially coefficient of friction times the mass times gravity times cosine of theta. Mg is force weight, cosine of theta. That gets plugged in. This information gets plugged in for force normal. So this is equivalent to this. And we're going to take all the stuff that force of friction is equal to. That's all of this stuff. This force of friction. And we can plug that in. Over here for force of friction. Now H is equal to some component of L. We want to find L, so we want to get H in terms of L. We can do that through our angle, because sine of theta is equal to our height over our slope length. So essentially H is equal to L times sine of theta. L sine of theta. So we can take this, we can take this and plug that in for our H. And we can look at K and say, well, Hooke's law says that force due to a spring is equal to K times delta X, and if we know this force, which we do, we know the displacement that it takes, we divide both sides by the displacement, and we know that K is equal to force over displacement. So we can take that and plug that in. We can take this and plug that in for K. And when we do all of that, what does our formula look like? It looks like this. And where did all this stuff come from? So we knew that K was equal to this, so we plugged it in here. We knew that H was equal to this, and we plugged that in right here. And we know force of friction was equal to this entire thing, and we plugged that in for friction. Now we can go about simplifying this expression. You'll notice that an x term cancels out here, a delta x term cancels out here, and I'm also going to multiply, and so you have over on the left hand side f delta x over 2, and we can start pulling out terms and trying to isolate L. The reason we're going to isolate L is that's what we're actually trying to find. If we look back in the problem, we can see that we're actually trying to find how far up the incline that the sphere goes. So we're trying to find this L, so we want to isolate L, and we can isolate L by pulling it out of this entire equation, of this right side of the equation. When you do that, you're left with force times the spring compression over 2 equals L times mg sine theta plus mu mg times cosine theta. And divide both sides by this entire term to isolate L. You're left with this mess, but this mess can also be simplified by pulling out mg from both sides, factoring that out, and you're left with this term. And we know all the numbers for this. We know what force is, we know what force is, we know what compression distance is, we know what the mass is, we know theta, we know the coefficient of friction. We know all this stuff. The force, if we look back at the problem, compression force is 15. The compression distance was 35 centimeters or 0.35 meters. 0.35 meters. Again, we're going to put everything into our standard units. Going back, mass is equal to 50 grams, which is 0.05 kilograms. Theta was 10 degrees, and the coefficient of friction was 0.1. 0.10. So we can plug all these numbers in and solve for L. When you do, plug them all in and solve for L. Plugging in your numbers, make sure you follow your order of operations correctly. Don't try and plug this all into a calculator. It might take you a couple steps. It took me a couple steps. So L is equal to 19.7 meters. Again, just to note, you could have, plugged all this information in here, up here, but you'd have to get numbers over here, plug in. You could do it that way. Again, I encourage you to try to start manipulating the letters to come up with an expression for what you're trying to solve for. and you can eliminate mathematical errors a lot easier.